Hey, how you guys doing today? This is Colin, also known as CYIT on YouTube. And today we'll be doing a PCB design. This is a Fields Lab STM32 Microcontroller PCB design, full tutorial in KiCad. So let's just go ahead and get started. So as stated earlier, this is a KiCad tutorial. And I really want to give a background on what exactly is KiCad. So KiCad is an open source software. I think what that means is it's free and it's a software suite. So it has many softwares to do a single job. So we can go ahead and design a schematic. We can lay it out on our PCB. We can get physical components. We can view it in our 3D viewer to see what it'll actually look like before we get it in hand. And then we can go ahead and generate the cover file, send it out to PCB manufacturers, and then get our physical boards so that we can actually use them. So I think that's pretty cool. That's our KiCad, just background information. And then now we can get into our first step, which is our schematic capture. So here's a look at our full schematic capture, designed by Phil. What I did is I just followed along through YouTube and learned as much as I can in the process. Keep in mind, this is a what did I do to learn electronics channel. So this is just like a tutorial overview, or a description through the lens or the way that I see it. So first of all, as you can see, we have this big microcontroller, because this is microcontroller PCB design. And this is an STM32 F103C8T6 microcontroller. And it's in the STM32 microcontroller family, designed by ST Microelectronics. It's a 32-bit ARM Cortex-M microprocessor. So 32-bit meaning that it can execute instructions 32 bits at a time. ARM is the microcontroller architecture that we're using, and then Cortex is the type of processor that we're using for our microcontroller. Now, I know some people watching this video may not even know exactly what a microcontroller is, so I'm here to tell you. A microprocessor is just a processor and it computes calculations. However, a microcontroller is a microprocessor, but it also includes peripherals. It also includes memory. That's where we get that 32-bit from. So it's just a lot more things that we can do with it. And this is because it's meant to perform tasks or perform controls within a larger system. All right. Okay, so now that we spoke about what a microcontroller is and we know exactly what microcontroller we're doing, we can go ahead and we can describe our schematic. So first of all, we have our VSS and VSSA here. This is our ground for our digital components, as well as our analog components inside of our microcontroller. And then if we go up here to the top, we have VBAT, VDD, VDD, and VDD. And this is power to our digital components inside of our microcontroller. And then VDDA provides power to analog components inside of our microcontroller. So if we come up here, we have 1, 2, 3, 4, 5 capacitors. The 4 here, C4, C5, C6, and C7 will be decoupling capacitors. And we have one of each for our VBAT, VDD, VDD, and VDD. So if we take a close look, 4 decoupling capacitors and then 4 power inputs. And our decoupling capacitors, what they're for is they provide a path for high frequency noise to go to ground, so that we don't affect our input for our digital components. And they also provide quick jolts of power when we need it. They store energy and release it when we need it. Now here we have a bulk decoupling capacitor at C3. As you can see, this one is 10 microfarads, whereas the rest of our decoupling capacitors are 100 nanofarads. And our bulk decoupling capacitor does somewhat similar to what our decoupling capacitors do, but this one is more energy storage focused and released when needed. That way we can smooth out variations inside of our power supply. So if we take a look here, our VDDA is separated as far as power source or power input is separated from our VDD. And that's because our VDDA, or the power to our analog components, are more susceptible and more sensitive to noise. So if we take a look here, obviously we have a decoupling capacitor here at C8, but we also have an additional pi filter with the ferrite bead. And because this is more sensitive, we have this ferrite bead to dissipate additional high frequency noise in the form of heat. So that's why our VBAT, VDD, and VDDA are separated. Now, if we come here to pins 5 and 6, we can see our crystal oscillator. And our crystal oscillator is just our clock for our microcontroller. And that just provides timing, and it synchronizes all of our operations and instructions for our microcontroller. If we look on pins 5 and 6, we can see that we have the net names HSE out and HSE in. And HSE signifies an external clock. It stands for high speed external. So it signifies a high speed external clock. And in our case, it is high speed because this clock, or this crystal oscillator, is 16 megahertz or 16 million clock cycles per second, right? So that's a lot. We also have 2 load capacitors, and these load capacitors just allow our crystal oscillator to oscillate consistently and accurately, and they allow our crystal oscillator to operate at its resonant frequency. Now, if we come over here to our pins 32 and 33, we have our USB universal serial bus. And I think what's cool about our USB is not only is it a communication protocol, so we can communicate to our microcontroller through our USB, but we can also get power through our USB. So in our case, we'll be getting power from our USB. This is a USB micro, and that power is going to be VBus, and it'll be 5 volts coming in. All right, so we come here, we also have, as you can see, we have USB_D plus and then USB_D minus, and these are differential pairs. And differential pairs, what those are 2 signals with equal voltage but opposite polarity, right? So they're the same voltage level, but one is negative and one is positive. And this is done because any noise or interference that's common to both signals can be canceled out that way. And that just allows for, better communication across longer signals or longer wires. So that's what differential pairs are. And then as you can see, we also have a 3.3 volt pull-up resistor connected to our USB_D plus signal. And I want to say this is because when communication is coming from our USB, I want to say it pulls the wire down. So this pull-up resistor just provides a default state when there is no communication being transmitted. Our default state for our USB-D plus is high, or is 3.3 volts. Now, we have a few more communication protocols over here to our left. We have first I2C, which stands for, it may be I2C or I2C, but it's integrated circuit. And this is on our pins 21 and 22. And like I said, this is a communication protocol. So we're going to go over a few things. First of all, this is a synchronous communication. So that means that the device and our microcontroller, they're communicating with the shared clock signal. And that clock signal will be coming from here, I2C2_SCL. And SCL stands for serial clock. I want to say it stands for serial clock line. And just like our crystal oscillator, this just provides synchronization and timing for our communication. And then not only do we have our serial clock line, we also have a serial data line here. And this line is used for transmitting and receiving data, so to and from our microcontroller. So it'll all be on the same line. And then if we want to go over what serial is, it means that the data will be transmitted sequentially bit by bit over that line, so one by one. Now we also, if we look here, just as we have pull-up resistors on our USB, our universal serial bus, we also have 2 pull-up resistors on our inter-integrated circuit lines. And that's because these lines are open drain, meaning that when data is transmitted across these lines, they're pulled down, but there's nothing to pull those lines up. So that when data is transmitted, the lines are only being pulled down. So when no data is being transmitted, we want these lines to be high by default. So we just have 2 pull-up resistors connected to 3.3 volts to pull these lines high. Now we also have UART. Like I said, these are all communication protocols. UART stands for Universal Asynchronous Receiver Transmitter. And what asynchronous means is that there is no shared clock between our two devices. So our microcontroller and whatever device may be sending and receiving data, or whichever device we may be connected to or communicating with, they have no shared clock signal. So that's what asynchronous means. Now, our UART is also a serial communication protocol. So like I said, bit by bit, one by one, sequentially over our wire. And then as you can see, we have a TX and a RX wire, no clock signal, keep that in mind. And our TX is for transmitting, and then our RX is our receiving signal. Now, if we come back over here, once again, next to our USB, we'll have our SWDIO and our SWCOK or clock. And this is our serial wire debug. And it's used for programming and debugging of our microcontroller. Our SWDYO is our serial wire debug input output. So this is a bi-directional data line. It's for input and output, that's in the name. And we also have our clock here, and that's just for synchronization, just like our crystal oscillator, just like our I2C clock. So we can also say that this one is synchronous as well. So if we take a look up here next to our decoupling capacitors, we can see that we have in reset, and in reset is short for not reset, and not reset signifies an active low signal. So what this means is that when our not reset is pulled low, our microcontroller will go ahead and reset. Now, I know some of you may be asking, well, if it's reset when it's pulled low, wouldn't we want to have a pull-up resistor so that its state when it's not being reset is high? That is a great question, and that is true. But our STM32 microcontroller has an inner pull-up resistor, so we don't have to add an additional one. So I know what Phil had us do is we just attached a line or a signal to it, and then we added a capacitor, and this capacitor will attenuate high frequency noise sitting this ground so that we don't inadvertently trigger our reset, our in reset signal. All right. Now, our last signal over here will be our boot zero. And our boot zero is connected to a switch, as you can see. And the way boot zero works is if boot zero is low, then our microcontroller will boot up from our main memory, and it'll, just, I guess you could say, like, continue regularly scheduled programming. So nothing will change. It'll just boot up as scheduled, how it's supposed to, and we'll get regular operation of our microcontroller. However, if we move this switch over to our 3.3 volts here, what'll happen is our microcontroller will enter a special bootloader, and this will allow us to, I guess, program our microcontroller. We can change our operating system or upload new firmware onto our microcontroller, and we can kind of do things that way. And then if we just kind of talk about what exactly is a bootloader is responsible for placing our operating system into the main memory of our processor. All right. So when boot zero is low, the operating system that will be placed into our processor is the original operating system. But when boot zero is high, we have the opportunity to change that and boot from maybe a different OS or a different firmware. So last but not least, we have our power supply, and our power supply is a linear regulator. And this power supply will take a higher voltage, that higher voltage being B bus, coming in from our USB, which is 5 volts. and it'll take that and it'll change it to a lower voltage at V out, which is going to be 3.3 volts. Now we also have a diode here, and this is a light emitting diode, so it'll be a red LED, and it'll just let us know when our microcontroller is on. And then we also have a current limiting resistor here, which makes a lot of sense. 1.5 kilo ohms. Now here we have two decoupling capacitors as well, and that'll serve the same purpose as every other decoupling capacitor in our microcontroller. It'll attenuate high frequency noise, sending it to ground, and then also provide power when we need it. So that is the basic outline, or what I did is I provided a basic understanding of our microcontroller schematic design process. And next we'll move on to our PCB layout and talk about that a little bit as well. Cool. Okay, so we're on to the next section, and this section is going to be our PCB layout. So one major difference here is we finally had a chance to use the footprint assignment tool inside of our KiCad, which I spoke about earlier. So if we take a look at our schematic, we can see capacitors, we can see resistors here, these little boxes. We can see our microcontroller. We can see our capacitor again. We have a switch here. We have a USB, and we have voltage regulators. We have all of this stuff, all of these components, and they're just kind of basic. But when we go over to our PCB layout and we take a look at those components again, those components are different. So this is what our footprint assignment is. We had a chance to assign real world physical components to the schematic, to our PCB layout from our schematic. And I think that's pretty cool. So if we just want to, take a look at this, and starting out, what we did is we first just took our microcontroller, because when we first got this, it was just a collection of parts, and they were in no order. So first what Phil had us do is we just took our microcontroller and we put it off to the side, and that was the baseline for our board. We were going to make everything or design or lay everything out around our microcontroller. All right. So after we placed our microcontroller, we went ahead and we placed our decoupling capacitors, C7, C6, I want to say, C5, C4, and we obviously placed those close to our microcontroller. We placed them close to our microcontroller, and then we also did our best to line up power and ground. So if we take a look at this, we can see that this is 3.3 volts, and this is also 3.3 volts on my capacitor, and then this is ground here, and this is also ground on my microcontroller. And it's like that for all of our decoupling capacitors, and that's because we're looking ahead to routing. We're placing everything and we're keeping routing in mind, because we want routing to be as simple, as easy, and we want it to flow. We want it to be as simple as possible. And then that is the same. That also goes for, so I know we just spoke about our VDD decoupling capacitors. Here is our VDDA decoupling capacitors, and it's the same thing. So we have 3.3 VA here and 3.3 VA here on pin 9. Make it very simple for component routing. And then close by, we also have our additional filtering for our VDDA components in our microcontroller. So this is our pi filter, ferrite bead, and 2 capacitors. So after we went ahead and placed our microcontroller, we placed our decoupling capacitors. Next, we placed our crystal oscillator, or our clock. Here we also have our 2 load capacitors close to our clock to allow it to operate at its resonant frequency. And we placed this first because, as we know, our clock is a sensitive component. It changes states multiple millions, 16 million times to the exact each second, right? So it's going to be a very sensitive component. It's susceptible to noise. It's susceptible to interference. So we wanted to kind of place that first and give it its own space, and just make sure that everything was going to be working just fine with our crystal oscillator. So after that, we went ahead and we placed our USB, our universal serial bus. And as you can see, our USB is placed near the end of the board. We're going to want to plug this in for our V-bus power, our 5 volts. We want to make sure this is easily accessible for the user. So that's why we have our USB on the edge of our board. And then if we also take a closer look, this is our pull-up resistor that we had connected to our USB_D plus line, and it's in line with our USB-D plus. So here we can see USB-D plus, and we come over here. This is also USB-D plus. So like I said, keeping routing in mind, this will be easy to route from here, our microcontroller, USB-D plus, straight through to our resistor, our pull-up resistor, and then straight to our pin on our USB. So now, if we zoom out a little bit, we have our UART, we have our serial wire debug, and we have our I2C. And the way we place those is we wanted to place them near the relevant pins. So if we take a look here, our serial wire debug is connected to pins 34 and 37. So here is our serial wire debug, and here is our pin 37, and then here is our pin 34. So we wanted to make sure, like I said, looking ahead to routing, it's easy. It's going to be easy to route from here to here and from here to here up to our serial wire debug. Same thing for our UART. If we take a closer look, our UART is pin 42 and 43. So therefore we have our UART connector directly over those pins on our microcontroller. And then if we come down to our I2C, which is pins 21 and 22, we take a closer look, 21 and 22 here. And that's going to be easy to route straight down from our microcontroller to our I2C. And then we also have our two pull-up resistors directly in line. That way we can route from our microcontroller directly through our pull-up resistors and then to our I2C connector. So next we have our linear regulator, and our linear regulator was placed there for a reason. We wanted to place it close to the power supply, which is going to be the PCB connector. We wanted to place it close to the power supply, and that was going to be our USB connector. We'll get 5 volts from our USB that'll go into our linear regulator, and we'll get 3.3 volts out. Now we also have our load capacitors here, C1 and C2. Same deal as our microcontroller, placed close to our linear regulator. And then we also have our diode, which will let us know when our microcontroller is on and receiving power, as well as our current limiting resistor here, which is R1. So last but not least, we have our boot zero, which is here, and our boot zero won't affect our microcontroller operation. So that's the reason that we placed it last. We can just kind of put it anywhere we can, fit it where we can. And then we do have our switch hanging off the edge of our board. That way it's easily accessible by the user. We can reset it, whenever need be. And then we take a look down here at C11. This is our M reset capacitor, and it's not placed near the relevant M reset pin. And that's because this is considered a low speed signal. And that's because it won't be changing states often. We won't continuously reset and set and reset and set our microcontroller over and over again. Therefore, we could place it last because, like I said, it won't affect our microcontroller operation. So that is our PCB layout. We also went ahead and added some holes to our PCB, but for the most part, that's our PCB layout. And I know next we'll talk about our PCB routing, what we're looking ahead to when we were laying out our board. So here's the last section of our PCB design. We went ahead and designed a schematic. We laid out all of the components, and then this is where we routed it. So I want to talk about a few things that I realized while routing. First of all, we went ahead and routed our signal lines first. And the reason we routed our signal lines first is because they tend to be more sensitive to noise, more sensitive to interference, and therefore we gave those priority over our power lines, the same way we gave our USB and our crystal oscillator priority over everything else. The way that we can tell that we gave our signal lines priority over our power lines is the fact that we had the jump traces. So if we look here near our R1 resistor, as well as here near our I2C, we can see that we have power lines coming to Vias, going underneath our board where the ground plane is, and then coming back up. And that's so that we can get past this signal line, this I2C signal line, but not mess it up, not disturb it, not interfere with it. And that just shows that we had to do those signal lines first, and then we went ahead and we did power lines. Now we take a closer look, we can also realize that, or we also begin to notice that our power vias here, which is our 3.3 volt, and then our ground vias, like this one, our power vias are a lot larger than our ground vias. And that's because larger traces or larger vias have a lower resistance, which means they have a lower voltage drop, which means that they more efficiently carry power because they have a higher current carrying capacity or ability. And that will be the same when we're looking at our 3.3 volt or our power lines compared to our signal lines. Our power lines tend to be a lot bigger, i.e. 0.5 millimeters, whereas our signal lines are 0.3 millimeters. And that's for the same reason. Wider traces, lower resistance, lower voltage drop, more efficient power delivery, as well as a higher current carrying capacity. Now we take a look over here to our linear regulator. We can see that we have, you can either call them power planes or power puddles or copper planes. And this is the same thing, honestly. They're a lot wider, higher current carrying capacity, better power delivery. And this is especially important because this section here, especially where power comes in from our USB 5 volts and it comes to our linear regulator, this supplies our whole board with power. So it's important for us to have a low resistance, a low voltage drop, and the highest current carrying capacity in this area. So last but not least, I know I previously mentioned that we do have a ground plane, and that ground plane just provides an easy path for all of our signals to go to ground. Like if we take a look here, we have 1, 2, 3, 4. We have a bunch of ground vias, and those dig through the board and they go to the bottom of our board. And if we take a look over here where it says show field areas of zones, we can see that on the bottom of our board, we have a blue ground plane. So all of our vias are digging down into that ground plane. So that's everything that I realized while I was following along with the video, when we were doing the route and all that good stuff. I just wanted to go ahead and point those things out. Lastly, I want to show the 3D viewer because I know I spoke on that a little bit in the beginning and we hadn't had a chance to, take a look at it. So here is that 3D viewer, and we can get a look at our fully finished and completed schematic. All right, so we go ahead and zoom in. This is the 3D view of our schematic. I am missing my USB device, but that's okay, or my USB component. But this is like the most realistic view that we'll get of what our PCB will look like once it's fully manufactured. So here's the back, and we already seen the front. Here's the front again. So the only other step after this will be to generate the Gerber file, send it out to any PCB designer of our choice, and then we can go ahead and get this physically in our hands. So this channel was what I did to learn electronics. I think this Fields Lab video was extremely helpful, especially because I got an embedded systems internship that I'll be starting soon. And if I think right, or if I'm on the right track, I'm pretty sure that it'll be microcontroller design as well as hardware coding, or embedded coding. So I really just wanted to kind of get a jump on that, and I think it falls right in line with what I did to learn electronics, and then also my journey from having no knowledge to being an expert in electronics. Right. So hey, if you guys liked the video, if you learned something, feel free to like, comment, subscribe. You guys have a great rest of your day.